Welcome back, Calcsters. Today in 1.2, we get to deal with the properties of limits. Now, we have a bunch of objectives throughout this section, and we're going to get all of them. Here's what I'm thinking I would like to do. Instead of making you guys graph all these little pictures and stuff, I am A-okay with just using Desmos. And as long as we have the definitions written down and you guys could pick out a linear or a constant or any of those types of functions, we should be okay without having to have any of the big pictures in your notes. Thoughts? That we don't have to do a bunch of graphs. Okay, so we are going to have a ton of basic properties first, and then we'll start getting crazy with it. So in 1.2, our first topic of the day is going to be basic properties. And before we go to the graph, I want to see if just your intuition is there for these. So we get a bunch of theorems, and we'll get the two most basic, and then we'll dig on from there. So check it out. Our first theorem right off the bat. This is the limit of a constant. Limit of a constant. Cool. So check it out. Given, and I'm going to try to write this in less words than your book does, but just so you know, the book does have all these as well. If we get some function, f of x equals, I don't care what number it is, let's say it's a, and I'm going to use a capital A specifically. If I have some constant function, can you tell me what the graph of it looks like? So it's a straight line. Is it slanted, vertical, or horizontal? Horizontal. So does it ever change a y value? So no matter what value of c we put in there, if this function of f of x, I asked you to tell me, hey, find me the limit as x approaches literally any number c of this function, f of x equals a, which I will use proper notation for this. There's my function. No matter what you plug in for c along a horizontal line, what value should it spit out at us? A, every single time. There's no other option. Our function just doesn't change. Cool with that idea? Like, I hope that's obvious to some degree. All right, next one. What if, and these are all theorems, I'm just going to do a tilde, and then I'll tilde, and we're just going to write them all instead of THM every time. Is that okay? Okay, they're all theorems. What if we wanted to do the limit, and I'm going to just try to write it out here, the limit as x approaches c of some function, and let's say that this one was x. A nice linear function. Now you might be thinking of the graph of y equals x in your head. If you are, awesome. If you aren't, awesome. I'll sketch a small graph of it, knowing that you do not have to. Here it is. If I go to 1, I know the point 1, 1 is on the graph. If I go to c, any arbitrary c, what's the y value it should spit out at me? I think it would be c again, wouldn't it? For any whatever you plug in, because it's always the same. Which means no matter what c value we go to, if we're taking the limit of a linear function like this, what should it give me? It's x or c? C in this case, but I think that the logic is there, Sean. I think it's just a goofy thing with the wording. Okay, now to make a little bit more sense of this, I'm going to just make sure that we have our thing here, and we'll do an example off on the side, just right next to it, just to show how easy this is. I want the limit as x approaches pi of x. Thoughts? Pi seems reasonable, right? In fact, it is exactly pi. Okay, the limit of a linear function is super chill, super easy to work with. All right, should we get on to some little crazier ones? Sweet. Anything shocking for anybody yet? All right, and I'm trying to remember where we saw this last year, but it'll come to me here pretty quickly. All right, next one. Let's say that I wanted the limit of a sum. So if I take the limit as x approaches c, and I wanted to do something like f of x plus or maybe minus another function g of x. If you got to write these rules, anybody have a strong opinion of what you would want it to be? Now, I cannot remember, I think it was when we were doing summations last year. I'm going to state something. I want you guys to see if we can finish it. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. So, anybody look at this and see that it kind of looks almost like distribution? Boom, it is. We would first take the limit as x approaches c of which function first? F of x. And I'll do it in, so it's really clear what the argument is. I'll do brackets since that's what I've been doing. Plus or minus, what do you think should come next? The limit as x approaches c of which function? Good, loud and confidently, I heard it whispered. G of x. Just like you would likely expect it. The limit of a sum is a sum of the limits, or the limit of a difference. Sean, question? Yeah, I changed it to a bracket and didn't take the time to erase because apparently I have no patience. No, you're good. That's my bad, not yours. Reasonable. Okay. We're going to do a bunch of examples afterward. I think I changed course like mid-thing just so that we can get all of them out, and then we'll see how well we can use these. Sweet. All right, let's keep getting crazy. What do you think the limit of a product is going to be? The limit of a product is the product of the limits. That seems pretty reasonable. So I want you guys to finish this one on your page, and I'm going to come around and glance. I want the limit as x approaches c of f of x times g of x. Show me what you expect this rule to turn into. Notice, very clear multiplication. It is not a compose. Cool. All right, I'm going to come. What's eavesdrop, but with your eyes? What's the phrase of that? Yeah, I'm not going to use that word. I'll come around and look at your pages. And at least 3 of you, shout out to Riley and Mickey and Fern, had something like this starting. I didn't see what the conclusion part was, but we have the limit of f times the limit of what? Boom. Is this what you guys all had on your pages before I wrote it? Love it. Okay. We're going to start getting a little bit weird with them. Just a little bit. Okay. These first 4 rules. Thumbs up. You think you can memorize these 4? Thumbs down. If not yet, that's okay. You will memorize them with practice, I assure you. Any part of these that seems super crazy challenging yet? Okay. So let's keep kicking. We get a lot of these. So here we are. I want to do the limit as x approaches c. And we're getting crazy now. I want the argument to be k, some number k, times f of x. Notice it's not a function times a function. It's just this. What could we do? And I know that it's like a challenging question because it's been a while. And when I walk away, the audio trails off. What could we do with a constant multiple like this when we dealt with summations last year? I think we moved it somewhere. Outside, out to the front, yeah? Now, I'll tell you, these are really, really closely related to summations. It's just a different point of view, a little bit different question, but the same basic concept. Sean, nice job remembering that. Constant multiple does indeed just come right out of the limit. So it becomes k times the limit as x approaches c of that lovely function f of x. And again, we'll get examples, but I want you to have a nice big comprehensive list, and then we'll knock examples when you can reference that list. All right. This one, getting wild. I want us to take the limit as x approaches c, and we're going to do the nth root of the function f. So we'll say it's the nth root of my function f of x. Okay. It's about here where my intuition starts to, I wouldn't say necessarily be wrong all the time, but it is definitely not as natural. Gut feeling, anybody but Abigail, because I see that you're following along, which is awesome. I appreciate it. Anybody have a gut feeling for what might happen here? So let me rephrase that, because I think everybody probably has a gut feeling of some sort. Don't care if you're confident about it. Who haven't I called on? Kalisha, we made eye contact, and I saw maybe some not profanity. What do you want to happen? What do you think would happen? When you say under the N. So like the radical goes around everything or it just disappears? So disappears is a good thought. I'll tell you, it's not quite the right one, but I appreciate your willingness to volunteer it. If we're taking the limit of the nth root of this function, we're just going to wind up doing the nth root of the entire limit. So the limit of a root is the root of the limit. It's that same language. It's not as nice, but all that means is that we're simply going to take the nth root of the entire limit. And I'm kind of holding off. If you guys ever want to prove these, I'm more than happy to, but we would be pushing a little bit past calculus into what's called analysis. The limit of a root is the root of the limit. Cool. Now, there is a little caveat. What do you think the index n of our radical needs to be? Would we let it be a -5, you think? A -5th root? Probably not. What's the first number that you're going to use if we're doing with radicals like this? Square root. It'll start at the square and then count up from there. Okay. Seems doable? Maybe. Can't get a good read on you guys. It will be doable. We will do it. All right. Here we go. The limit as x approaches c. I think we have like 2 more. Yep, cool. So let's say I wanted to take the limit of this big gross function f of x, and we're going to raise all of f of x to the power of m over n. Okay. Before we expand, really important observation. This looks wildly different than the one that we wrote just a moment ago. But what do those ratio exponents or rational exponents really do? What does it mean to have something to the power of m over n? So I'm going to pause the video here in just a second. With your neighbors, I want you to tell me what this becomes. Cool. I'm going to give you a minute. How do we do that? What is that? You guys have calculators if you want to play with real numbers. We're going to see if we can recall how do rational exponents work. Maybe since this is the same as the nth root, does the same rule apply? Seems like it'd be natural. Like it'd be weird if it didn't. What do you think we're going to write here then? If I take the limit of a function to a power, and this one doesn't, it's not as nice to get this worked out. What should I raise to the power of m over n after I do the limit? Or to do the limit, rather? What happened to the power of 1 over n here? It was on the function, and then it went around everything, right? What should this power do? Should go around everything. So here we go. You just take the limit of the nicer function, and all of this gets raised to the power of m over n. Okay. We get lots of rules. You will memorize these eventually. Like, it'll become second nature. There's nothing crazy that happens in here. Couple more, and then the rest is just going to be examples. I don't think I'm going to give you homework today, but we're going to work a bunch of examples in class. Okay, are these all fitting on one page for you guys? Fantastic. Okay, this next one, I haven't been writing the name of these. I'm going to for this one. Polynomial limits. Now, polynomial functions are those that you guys have dealt with over and over and over. They're nice and smooth. They don't have any sharp turns. They're continuous, so you could drag your pencil forever and you could graph the whole thing. They're the nice ones. X, x squared, x cubed, any of those are all polynomials. Now, given a polynomial function, and I'm going to use p for polynomial, turns out that there's this really, really handy idea that if you get the chance, we should use it. If we take the limit as x approaches c of some polynomial function, and I'm going to call this p of x, and if you need it, I'm just going to say polyfunc right here. If, because it's continuous and it doesn't have any weird things, my values should approach whatever the value is of my function. Which means, Rafa, and I saw you nod in agreement, if I want to know what happens to this function p as I get close to c, how would you word that? How would you write it? So I'll sketch over here because it will help, because it feels like a hard question. I promise it's easy. Is this a polynomial function that I've just drawn? Does it have any sharp turns, anything weird about it? So it has turns, but they're not like pointy, weird turns or anything like that. It's nice and smooth. I can draw it. This is my function p of x. If I wanted to know what happens as I get close to this, do you agree that they're going to get really close to this y value? And if I just want to know what does this value spit out when I plug in c, does it seem reasonable that this is what it is? Okay, you will hear me refer to this, and we will see it again. This is called direct substitution. This is the nicest possible type of limit that we can evaluate. If you get a nice polynomial function, turns out it is exactly p of c. If you look up at your notes, when we did the limit as x approaches c of x, our linear function, did it just spit out c? Or a, I guess, in ours? That's the exact same rule. We're just pushing out a little bit further at this point. Okay. We have one more, I think, is all that I have. Boom, one more, and then we get to do a bunch of problems. Okay. Last one, and then we'll get to it. Who haven't I called on? Have I called on every single person? Angel, I haven't called on you yet. Thanks for raising your hand. All right, check it out. We are going to deal with a rational function. I want some function that has f of x over g of x. Okay. Gut feeling if I ask you to take the limit of a quotient. Angel. So we're going to back up for 1 second. I just want to remind of the way that we say some of these. The limit of a sum was the sum of the limits, right? Like that's what this one says. The limit of a sum is the sum of those two limits. The limit of a product, that's what I'm taking the limit of, is the product of the limits. What do you think we're going to say about the limit of a quotient? It's the quotient of the limits. You got it. This is as easy as saying it's the limit, and this is the ugliest thing we'll have to write today, as x approaches c of f of x over the limit as x approaches c of g of x. Is there anything, Fern, that you think we should probably include about this denominator? The limit as x approaches c of g of x in this situation cannot be 0. Anything else is fair game. All right. So here's the challenge that I would like us to knock out. We're going to do a bunch of examples. But instead of just doing it, here's the one that we defined an example of it immediately, we're going to do examples where it is going to be your job as a class, as individuals, pairs, however we're talking about these, to figure out which of these rules we're going to apply. Okay, that's the hardest part of these. The rules themselves are pretty straightforward once you get a little practice. Determining which rule can be more of a challenge. So let's knock out a bunch of these bad boys here. I want us, ooh man, piecewise with absolute values. That's what everybody wants, right? All right. Enthusiasm. All right, here we go. Examples. I want us to evaluate each of the following. Evaluate. And we'll do a few together. And realistically, we'll probably just do a bunch together right now since we have all this time. I want us to find the limit as x approaches a of the argument of this limit, or what we're actually taking the limit of, is going to be x squared minus 2x plus 1, x squared minus 2x plus 1 squared. Blah. Okay. Now, we didn't name them all, and I'm fine without naming them all. Does everybody have this example written down? So I'll wait a second. When you're done, I don't always do this. We just set your pencil down just so I know that you're done. As you're waiting for me, I want you to check your list of all those rules that we just saw and see, is there a rule that fits this problem? If everybody has it, I'll scroll up, or I'll just zoom out so we can see mine as well. I'm going to put numbers here just so we can refer to them together as a class without getting too crazy. I wouldn't number yours. We'll say 1, 2, 3, 4, 5, 6, 7, 8, 9. Do any of these seem to line up with this? 7. Gosh, Ralph, I agree with you. Is this a fraction on the exponent? It's over 1. It doesn't look like it, but it certainly is a fraction, right? That's to the power of 2 over 1, which looks exactly like Rule 7, the limit of a power. So if we're trying to do this, the limit of a power, according to this, is the what? The power of the limit. Now, as we dig into this thing, let's go a step further with this. As we look at it, man, I know that right off the bat, and I'll zoom back in, the limit of a power is the power of the limit. Okay. Can we rewrite this then as the power of a limit? And this is going to feel tedious, but I promise there's benefit to it. I'm just going to write the entire thing in the parentheses. X squared minus 2x plus 1. And then I do what to everything? And then I square it. Okay. Going further, we might get different variations of this problem. Anybody look at that expression on the inside and think, man, I can factor it? Specifically, x squared minus 2x plus 1. Does anybody's first thought say to factor it? Probably not, right? And that's okay that it doesn't. Is this a polynomial function? Is this a nice, easy to deal with thing with nothing crazy with it? So what should I do? What did we call this? I didn't write it down, but I made it a point to mention it. It's like I literally just replace the x with whatever my limit is, right? On a polynomial. Is this a polynomial? So anywhere that I have an x, what's it going to replace to? A. Okay, so right off the bat, this thing could become a squared minus 2a plus 1. And I've already done the limit, so notice I didn't write the limit again. We've done our direct substitution. And I'm going to start writing that here, direct sub. That's exactly what we've done for our polynomial. And then what happens up here still? Squared. Okay, here's my challenge for you. I want you guys using your fancy TI-89s. We're going to play in the algebra menu for a second. Anybody not have their calculator today? Okay, if I wanted to do some algebra, where do you think I would get there from the home screen? Louder. F2. So check it out. Here we are. We have F2. What are we trying to do? We're about to square something, right? Is that called expanding it or factoring it? Expand. We're trying to make it bigger. Let's expand. Now, my calculator could probably understand it if I told it to do it with A. But what letter do you think is probably easier to do? X. So I've already forgotten the function, though. X squared minus 2x plus 1. So here we go. In parentheses, x squared minus 2x plus 1. And I'm going to square it. You have to close your parentheses. Notice I had another set inside because whatever I'm squaring, I need to be clear that everything does get squared. So here we go. We could do this. Okay. This is not the only option for how to do this. In fact, when I look at my text, I'm doing an additional example that's not in your guys' book, but it shows me that this is not the answer that they have. We'll talk about the answer that they have. We're both correct. So Only thing different is if I used A, what are all these going to be? A. So kind of tedious, and it might not feel like we're doing much here, honestly, but I think it's a to the fourth minus 4a cubed plus 6a squared minus 4a plus 1. This is not what your textbook says. Now, this option, if this was a free response and this is the answer that you gave on a test, did you get something different, Riley? All right, so we're going to re-expand a simpler one, but just to get practice with it, okay? So here we are. Just for practice, I want to do x plus 1 squared. So I'm going to hit F2. And if I was doing x plus 1, I'm going to select 3 because I want to expand this thing to be big. And then in parentheses, if I want to square more than one thing, I'll add them in. So here's a parenthesis, x plus 1. And I could raise this to the 5th power if I wanted. And then I close it. Now on our example, it wasn't x plus 1. It was this terrible thing. I just happened to use x's instead. Okay, so once we're here, boom. Now, this problem is direct sub. It's kind of gross if you have to FOIL it out on your own, right? So I'm going to show you what the textbook proposes as their answer. And I want to know is how could we get here? So they claim on this one, they write it like this, a minus 1 to the power of 4. Okay, different, wildly different looking answer. And it looks like maybe they just took this and factored it. Now, I don't want to make you guys factor 4th degree polynomials. I think that that's not very much fun. However, can you guys find factors of 1 that add up to negative 2? Say it again. Negative 1 and negative 1? So if I wanted, right at the beginning, instead of dealing with this awful thing, if you noticed, I think we can factor this as x minus 1 squared. And it still gets squared because I'm just taking the power of the limit. When I do this, I can still plug in a. So no more limit symbol. A minus 1 squared. Squared. I've done my direct substitution. And what happens when you square a square? They multiply. So it would be a minus 1 to the power of? Same answer. Wildly different look. If you elect to factor first, maybe you'll save some time. Cool. Should we have you guys just try a few together? Sweet. Okay, I'm going to have like 3 examples here that I want us to work through. Ooh, man. You think you might have to use the F word sometimes? Factor, that is. The other one, of course not. Who would ever say such terrible things? Cool. Let's get crazy. Now, not going to lie, I'm going to give you guys a little struggle. Okay, it's good for you, I promise. I want you guys to evaluate together 2 problems. B is going to be the limit as x approaches, I don't know, let's get crazy, 3 of lovely rational function, x cubed minus 9x, all divided by x minus 3. I want you with your neighbors to try to apply the rules here. I'm also going to have example C up here. Once you think you have an answer for B, I want you to check. We're going to dive into some more complicated techniques at the start of class tomorrow, but I want to see what you guys come up with first. So on C, it's another lovely rational, and you guys can just ignore me until you've worked through B in all reality. Cool. Productive strubble. Strubble? Sure. Productive strubble is our goal. Okay, talk it out. Practice with this one. You run into problems, right? Even if you try to do the quotient of the limits. You can do the numerator pretty easily. It's 0, right? Is that right? 27 minus 20. Yeah, 0 over 0, but that's undefined. So we get a fancy technique. We are going to divide out. Divide out. GCF, if possible. So let's check it. I'm then going to just rewrite this a little bit to see if I can make this easier for myself before I do the limit. How would this factor up top? x times x squared minus 9 all over x minus 3. I have just taken the GCF of the numerator. Nothing divides out yet. However, in the numerator, I see something that's going to be crazy helpful. Am I done factoring? There's more factoring that I can do. What do you see, Abigail? Anybody else see the difference of squares up top? This right here, it factors further, I think. How does that factor? This is the limit as x approaches 3, and it's so annoying to have to write this, I know. It bugs me too. X times, gosh, how do you factor a difference of squares? X minus 3 is one of those factors. In the second? X plus 3. And this is still all divided by x minus 3. Okay, we haven't done the limit yet. We're just cleaning up the algebra. When we factor it like this, Kalisha, is there anything that you see that might fall out or divide out of this? So you're close. The x minus 3, because what's this x minus 3 over this x minus 3? Okay, which means when we get to our next line, let's just see what we have. We have the limit as x approaches 3 of x times x plus 3. Do I need to worry about quotients anymore? No. This is a polynomial. It's nice. I don't even have to expand it. Or you could think of it as the limit of the product. I'm just going to use the polynomial and just try my direct sub. If I plug in a 3 here, it'd be a 3 times a, what's 3 plus 3? What does this limit look like it's going to be? 18. Tomorrow, we are going to do 4 or 5 more examples of more challenging ones together right at the start of class, and then you'll have time to demonstrate your ability to do these. Cool. Later, Raiders. What's up, geometers? Fair. Do we have homework? Why?